Today we take another step on our seemingly never-ending journey to quantum physics. Last time we talked about the thermal production of light. That is, an object gets hot, it glows and gives off light. We saw for stars that temperature determined two things. It determined how much light came off per second in terms of energy, and it also determined what types of light came off. So we saw at low temperatures, we got mostly infrared and maybe a little bit of red. And then as we upped the temperature, we got a higher proportion of colors like the greens and the blues. We also saw that we got 16 times more total energy per second every time we double the Kelvin temperature. We can reproduce this in the laboratory using a wire inside a light bulb and just change the temperature of the wire, and we can change both the brightness, the power, the energy per second, and the type of light that we get, that is the color of the overall light. We can see that it forms a quasi-bell shape. We saw that one type of light was more prevalent than the others, but all types of light are present. Okay, some of them might be really, really low, and some of them could be pretty significant, but all the wavelengths are represented. We saw an equation to predict the peak wavelength. We saw a formula to predict the power. Both of these are based on temperature. We now want to talk about where the light comes from in the first place. Light is produced whenever you have a charged object accelerating. So we can take a charge, positive or negative, doesn't matter, and we can oscillate it, we can move it, we can accelerate it. And when it accelerates, the electric and magnetic field around that charge is going to be disturbed. It is the propagation of that disturbance through space and time, which we call light. Because of this, the thermal motion of charges is going to produce a quasi-bell-shaped curve, just like the distribution of speeds. Okay, so they're based on kind of the same idea that we got these random distribution of speeds based on temperature. And as these particles, charged particles, the electrons specifically, are moving around, they're producing light. All right, so we get this quasi-bell shape both in thermal physics and something very similar for the production of light. However, realize that some things can give off light without ever getting hot. Things like bioluminescent creatures, things like glow sticks and the LED lights that you might have up around your room. These glowing glow sticks are not hot. You would not give a little kid a 3,000 Kelvin object to wear around their wrist on the 4th of July. Somehow they give off light without getting hot. When we look at the light coming off of these objects through a diffraction grating, so we can see what wavelengths it's made up of, we don't see the familiar bell-shaped, quasi-bell-shaped curve. Instead, we see some colors are present, most colors are not. So we have tons of wavelengths that don't exist in that spectrum. But then we have some colors that exist with quite a lot of prevalence, okay? So in this case, you got a lot of red, we get some green and some purple, and a little bit of blue also. So make sure you understand when things give off light, because they're hot, you get all the wavelengths of light in different proportions, and the ones that give off light when they're not hot give off some wavelengths but not others. That's going to be a big clue later on to what's happening inside the atom. We can see this with these two types of spectrums, a continuous spectrum versus an emission spectrum. A continuous spectrum is what you get from a hot object. You'll notice all of the colors are present, including ultraviolet and infrared that we can't see, but all of them are present. One wavelength will be more prevalent than others, but all of them are present. It's continuous. with an emission spectrum, like we saw, some colors are there, most are not. This is what you get from a hot object. This is what you get from an object that is giving off light, but not based on temperature. We can produce this in the laboratory real easily by looking at an old Edison bulb, incandescent. That's the kind that has the hot wire inside of it that we saw earlier, versus a fluorescent, in which we are somehow using electricity to produce light without the intermediate step of heat and temperature. And when I use my diffraction grating on each of these light bulbs, you'll see the incandescent bulb produces a beautiful continuous spectrum. Whereas with the fluorescent bulb, I get a nice purple and then nothing, and then a blue and then nothing, and then a green kind of melding in with some others, but you can see distinctly that it is not continuous. There are breaks in this spectrum. We can make this even more clear instead of showing the entire bulb, which tends to be a big area and colors start overlapping, if we can just have a thin pencil of light. So what I did is I hit the light bulb behind the black piece of paper, and I just put a small slit in that paper, wide enough that we get maybe a pencil thin stream of light. And what we get with our incandescent bulb is a beautiful continuous spectrum. When I use the fluorescent bulb, this pencil of white light turns into distinct colors where others are missing. A more sophisticated analysis of the same bulb that I use is presented here. You can see this person created this back in 2007, and you can see the different bands, and they actually went ahead and plotted it out graphically. So you can see you don't have a bell-shaped curve. You have some colors occurring a lot, and lots of colors not appearing at all. You guys did this with mist air. You took bulbs, glass bulbs that had different gases inside of them, and you analyzed them after you excited them in a high voltage device. Here's what it looked like. I'm sure you remember seeing these. They're pretty interesting patterns that you would see in your chemistry class. So you can see this light gets broken up by the diffraction grating to produce the colors that make up that light. And the interesting thing is, if you have gases of different atoms, different elements, you'll get different patterns. So every time you look at hydrogen, you will see this. Every time you look at helium, you see that, and so on. So it's important to know that each element has its own fingerprint, its light fingerprint. That is a pattern of lines that are unique to that element. This is a fantastic tool that we can use to figure out what an element is, especially when we're looking at a star far away. If we can see a pattern like this in the star, we can tell what the star is made out of. Okay, I also want to make sure I distinguish between something called an emission spectrum and something called an absorption spectrum. Emission spectrum we already talked about. An absorption spectrum, you'll notice, is a continuous spectrum that is all the wavelengths of light with a few of them missing. And the crazy part is they line up with an emission spectrum for a certain element. So just to be clear, this is how you see an emission spectrum. You have your source of light, like a fluorescent bulb, one that is giving off light without getting hot. You view it through a diffraction grating, and that is what you see. For an absorption spectrum, you don't start with a fluorescent light, you start with an incandescent light, something that is giving off light because of its temperature. That light will have every single wavelength in it. You then pass it through some sort of material, a gas, if you will. Okay? Maybe it's a cloud out in space. And then you view it through your diffraction grating. and you'll notice that the cloud somehow takes away certain wavelengths of light. We will learn what all of this means in just a little bit, but for today, make sure you understand these three different types of spectrums. Continuous is from a hot glowing object. All the wavelengths are present. One wavelength will be more dominant than the others. Emission spectrum, most of the colors are missing, and then there are a few random colors which are determined by the element that it's coming from. Finally, an absorption spectrum has all the colors, but with a few distinct colors missing, and the missing colors match up with the emission spectrum for whatever type of material you're shining your light through. Somehow, this material, instead of giving off light, is eating that specific wavelength of light.